Alrighty, friends. This screencast is a big one. This is a theorem with teeth. Not only does it have teeth, it has serious consequences for us down the road. This theorem unlocks a whole lot of stuff for us. But before we can talk about the mean value theorem, we've got to talk about another theorem that's named for a guy named Michel Rolle. Michel Rolle. Oddly enough, Michel Rolle's primary contribution to mathematics was not this theorem. It just happens to be named for him. He was one of the early detractors from the calculus. And oddly enough, the only place you're gonna see his name anymore is in a calculus book. So that's neither here nor there. Let's talk about it. Suppose that y equals f of x is continuous at every point on a closed interval AB and differentiable at every point on an open interval AB. By the way, that allows us to look at functions like this, where you've got a vertical tan here and a vertical tan there, so we're not differentiable in between, we are differentiable in between A and B, but not at A or at B. We're continuous everywhere. We're differentiable inside in between A and B, but not necessarily at A and B. So we're continuous at every point on the closed interval, differentiable at every point on the open one. If f of A is f of B, then there is at least one number C in the closed interval in the open interval from A to B, at which f prime of C is 0. Back to the previous picture. F of A is f of B, so there has to be at least one place where the tangent line is horizontal. That's what Rolle's theorem says. There's a nifty proof for this that we should talk about. And the nifty proof for this runs off the fact that f has a max and a min on AB. F has a max and a min on AB, which is great because we know that that's true just because f of x is continuous. There was a theorem we talked about last time we were together that said if you're a continuous function on a closed interval, you have a max and a min. Well, there's only two kinds of places where that max and min could be. It could be at an interior point, or it could be at an endpoint. Well, if the max or the min are at some interior point, then we know that if the function is differentiable and it is continuous and there's a max there, then we have a derivative of 0. Can't have a cusp or a corner because we're differentiable. If there's a max at an interior point, derivative is 0. Well, what if it happens at the endpoints? Well, for the max or the min to happen at the endpoints, the function would have to be some kind of constant. And in that case, f prime of c is 0 for all c. Think about it. If the max and the min both occur at the endpoints, and the max and the min have the same y value, then the function has to be a constant function. And so the derivative is always 0. Let's confirm Rolle's theorem. Let's confirm Rolle's theorem for x to the 4th minus 2x squared on negative 2 to 2. So we've got to ask some questions. How do I know that this thing is continuous? How do I know that this thing is differentiable? And is f of negative 2 the same as f of 2? The answers to these are both yes, because polynomials are continuous and differentiable. That's easy. Is f of negative 2 the same as f of 2? A little bit of arithmetic tells us yes. So Rolle's theorem says if I have a continuous function, differentiable on the open interval, and if f of a equals f of b, then there has to be some value in between -2 and 2 where the derivative is 0. So I just have to find what that is. Oh, I can factor. And it turns out that there are 3 values of x, where f prime is 0, x equals 0, x equals -1, and x equals 1, and all of them are on -2 to 2. One would have been enough, but all of them are on the interval from -2 to 2. So we have confirmed that Rolle's theorem does hold for this particular function in this particular instance. Hey, while we're on the topic, oh, whoa, that's okay. Yes. I don't know what that was. Sorry, folks at home. Assumptions matter. What if the function is not continuous on a to b? If the function is not continuous on a to b, then I shouldn't be surprised that there's no place I can draw a horizontal tangent line. Similarly, if the function is not differentiable on a to b, then I should not be surprised that I can't find a place where I'm going to draw a horizontal tangent line. The function has to be continuous on the whole closed interval from a to b, and it has to be differentiable everywhere between a and b. The assumptions matter. And they matter because Rolle's theorem leads to the mean value theorem. And the mean value theorem says, suppose that f is continuous on the closed interval AB and differentiable on the open interval AB. Now, why do we have these hypotheses? Because we're going to use Rolle's theorem to prove this. And since we're going to use Rolle's theorem to prove this, we have to have the same hypotheses that Rolle had. Then there exists some c between a and b such that f prime of c is f of b minus f of a over b minus a. And I can hear you saying already, what the heck is that? Here's a, here's b. Let's take a look at the easy part. This is the easy part. This is the slope of a secant line. It's the slope of this secant line, the line connecting AF of A and BF of B. What the mean value theorem says is that there has to be some place where the slope of the tangent line is equal to the slope of the secant line. In this case, there are 2 such places. They don't have to be 2 such places. There has to be at least one. There has to be at least one. It's an existence theorem. Doesn't tell you where, doesn't tell you how many, just tells you there are at least one. There is at least one. This is that situation where average rate of change and instantaneous rate of change have to be the same for a continuous differentiable function at least one point. This is why if you drive on the thruway for 210 miles and it takes you 3 hours, it's an average speed of 70 miles per hour, at some point you were going exactly 70 miles per hour. At some point. That's the physical interpretation. There's a really nifty proof, and the really nifty proof says consider h of x, and h of x is f of x minus f of a minus f of b minus f of a over b minus a times x minus a. In other words, h of x is the vertical distance between f and the blue line. So h here is 0, and h here is 0, because the function and the blue line are in the same place. H here is 0. H here is pretty big. H here is pretty big. Pretty big negative, in fact. Wait a second. H is 0 here and 0 here. Rolle's theorem applies to h of x. H satisfies the conditions of Rolle's theorem, which means that for some c in AB, h prime of c is 0. But what's h prime of c? It's the derivative of all of this at c. So that's f prime of c. This is a number that drops out. This is a line whose derivative is its slope. And to get from this to our boxed theorem doesn't take long at all. The mean value theorem says if I have a continuous differentiable function on a closed interval, then there is some point where the slope of the tangent and the slope of the secant are the same. From a crank it out standpoint, find the c guaranteed by the mean value theorem for g of x is x squared minus 4x plus 4 on the interval from 0 to 3. Well, the mean value theorem says g prime of c has to be g of 3 minus g of 0 over 3 minus 0 at some specific point. Well, g of 3 minus g of 0 over 3 minus 0 is negative 3 divided by 3, and that's negative 1. What's g prime? Well, g prime of x is 2x minus 4, so g prime of c is 2c minus 4, and we can solve this fairly easily, and you will notice that 3/2 falls between 0 and 3 as required. This is a theorem with serious teeth. There are 3 big consequences, 3 very big consequences of the mean value theorem that we'll talk about when we gather. But for now, it's enough to get you practicing. Thanks, everybody.